Assalamualaikum warahmatullahi wabarakatuh. Good morning everyone. Today I would like to talk about our research with entitled Surface Roughness Analysis of Hot Turning AISI 4340 using the response surface methodology. I'm Cindy Hartita, student of Master Program in Mechanical Engineering, Sriwijaya University. In the manufacturing industry, machining is one way to produce large quantities of products in a relatively short time. In the machining process, the workpiece is a type of material with specific mechanical properties that's cut continuously by a cutting tool to produce the desired shape. Therefore, it is necessary to adjust the tool material. Machining aims to producing workpiece derived from ferrous and non-ferrous based materials, which go through a machining process using machine tools. Machining is a branch of machining that includes the machining process by removing part of the material from the workpiece. One type of machining is the lathe process. The lathe process is a process that is carried out by consuming the workpiece, by rotating the workpiece in a translational manner parallel to the rotary axis of the workpiece. Surface roughness, or commonly called roughness, is a component of surface texture. It is measured by the deviation towards the real surface average factor from the ideal shape. If these deviations are large, the surface is rough, and if they are small, the surface is smooth. In the machining process with a lathe, the surface roughness value is a very important factor in the production field because the measurement of the surface roughness value will determine in terms of guaranteeing the quality, accuracy, and precision of a component. To obtain the quality of the machining results from the turning results, finishing work is required by adjusting the rotation speed, in-feed depth, and in-feed step speed, which aims to achieve a standard number, namely the average surface roughness number with a certain level of surface roughness level. Response surface methodology, or RSM, is a set of mathematical and statistical techniques to design, improve, and optimize experiments. RSM is a valuable tool for studying interactions between different variables and for optimizing response with a minimal amount of experimental data. The goal of RSM is to build a model that optimizes the relationship between one or more independent variables and the desired response variable. This methodology is used in scientific and industrial research to improve product or process design, reduce costs, and increase efficiency. In the final stage, the optimum point is predicted using surface graphs and ANOVA. In this research, the variance analysis, or ANOVA, was used to determine the critical states of the cutting parameters. In contrast, the optimization of the parameters affecting surface roughness was achieved using the response surface methodology, or RSM, which is based on the Taguchi orthogonal test design. This research considered several independent variables, including cutting speed, feed rate, depth of cut, and workpiece temperature. An experimental plan is carried out with the design to get maximum quality results. Then, the quadratic model is used to examine the relationship between the response variable and the input variable. Furthermore, An analysis of the equations was carried out based on ANOVA. Then, the application of RSM can be done through a series of experiments with different variables. Response variables, such as yield of product quality, are measured for each trial. Once the model is fitted, it can be used to predict the response variable for new input values within the initial trial range. Finally, applying the RSM method, the best equation will be obtained, thereby increasing efficiency and profitability. Figure 1 shows that this graph compares the data obtained from research with a distribution close to the normal distribution. It can be seen that all points are located near a straight line, which indicates that the prediction of the response surface methodology is accurate. Figure 2, according to the results in graph 2, the residuals are randomly distributed, and the difference from the original observations remains constant across all y values. This shows no dependence on the difference in response to the average y level, so that it can be concluded that the model meets the requirement. Figure 3 is a perturbation plot which describes all the factors included in one response plot. This plot provides information on how the response changes when each factor is moved from a reference point, while all other factors are held constant and their reference values. The graph shows that the slope of factor B, namely the feed rate, is steeper than the slope of factors A, C, and D. This indicates that the response is more sensitive to changes in factor B, so it becomes an important factor to consider. From the results, we got the best mathematical equation shown in this slide. This mathematical equation is an essential tool for engineers and scientists in manufacturing because it allows them to estimate the surface roughness of a material under different cutting conditions and to optimize the machining process to achieve the desired surface finish. Data analysis shows that the calculated feeding rate is around 22%. Then, the depth of cut has a relatively lower impact on surface roughness, around 5%. On the other hand, cutting speed and workpiece temperature was found to have a relatively small impact on surface roughness, accounting for only about 3% of the variation. These results highlight the importance of controlling the feed rate while considering surface roughness as a target parameter. Conclusion: the data analysis is indicating that the feed rate has the most significant impact on surface roughness, accounting for approximately 22% of the variation observed in the data. This suggests that changes in the feed rate can result in a substantial difference in surface roughness compared to other factors. Following the feed rate, the depth of cut was found to have a comparatively lower impact on surface roughness, contributing to around 5% of the observed variation. On the other hand, both cutting speed and workpiece temperature were found to have a relatively minor impact on surface roughness, accounting for only about 3% of the variation. And in the context of surface roughness, RSM can be employed to determine the best mathematical equation that models the relationship between surface roughness and various independent variables, such as cutting speed, in-feed rate, depth of cut, and workpiece temperature. After analyzing the experimental data obtained through RSM, it has been determined that the quadratic model is the most appropriate mathematical equation to predict surface roughness as the dependent variable. That's all of my presentation today. Thank you very much for your attention. See you on the next conference. Wassalamualaikum warahmatullahi wabarakatuh.